Good morning, everyone. Thank you for joining our session today for OptiStruct for Composite Analysis and Optimization. I'm the moderator for today. My name is Darius Badinelli, and we have our instructor being Andrew, and he's worked with a lot of the OEMs around the Detroit area and also some of the university teams here. Okay. All right, everybody, let's get started again. I believe there was some people couldn't hear me, so welcome, good afternoon, and good morning to everybody in attendance. My name is Darius Badinelli, and I'll be the moderator for today's session. Today, our instructor will be Andrew, and he is the application engineer that works with some OEMs around the Detroit area and also with some of the competitive teams in Michigan too. Before we get started, I just want to let everybody know that you'll be muted. If you do have a question, please use the question tab on the GoToWebinar, and I'll be watching that, and if there's something related to the immediate topic, I will pause Andrew so he can answer the question, or we'll wait till later when we have a question and answer session. We are recording this session, so everybody who signed up for it and in attendance will get a link to this in an email later today, and so you can also share with members on your team. We will have two really short polling questions at the end. One will be asking when would be a time to offer these during your next build of your car, so we can make sure we can align that up so we can get even more attendance. Also, the second question will be asking if you would like to receive more information about this session or other sessions that we had, and then somebody from your region will contact you to see if they can help you out with that or set up maybe some more detailed training with your team. One of the questions that is asked a lot, so we'll just get to it right now, how to get, or is there a student version of the products you'll be seeing today? And the answer is yes. If you go to our home page and you go to the Academia tab, there is an option there to receive the student version, the free version of it. All you need to do is order it. Even though it's free, you'll give some information of where you're at, your information about your computer, and you'll be then sent, once it's approved, the necessary license file and a link to download. So it's free, and it allows you to work on models, FEA models of 10,000 nodes. If you do use our Inspire product, that one does not have any model limitation to it. So let's get started, and we'll change over to Andrew here. So again, thank you, everybody, and I hope you enjoyed today's session.
Hello, everyone. My name is Andrew Stankovich, as Darius introduced me. Thank you very much, Darius. And basically today we're going to be covering composite analysis and composite optimization. So hold on one second here while I get my screen up. Okay, so today we'll be looking at a student example of a composite monocoque. And so we're going to be going through all the different ways to set up composite analysis and many of the different features within HyperMesh, OptiStruct, and HyperView for post-processing. So I just wanted to start off real quick with going over basically the two different types of composite modeling. So when you model a composite in OptiStruct, the main element type that we're going to be using are shell elements. And so there's two different methods of representing the composite material, and those are the zone-based modeling and the ply-based modeling. In zone-based modeling, you have a property card that represents each unique zone of composites. So within, you may have many plies that all overlap, and within regions where all of the plies are the same, you'll have what's called a zone, and you can see that here visualized with all the different colors. This method is the traditional method of modeling composites, and it's easier from the standpoint of a solver because you have individual property cards, but once you start making modifications and doing optimization, it gets a little bit more difficult, and on top of that, it's not very representative of a real-world type of laminate. So the other modeling method that we have is what's called ply-based modeling. So I'll turn on the composite layer view here, and I'll show you what ply-based modeling looks like. So in ply-based modeling, you're going to be looking at every individual ply as kind of its own property. And instead of realizing these zones that have similar properties, you're going to keep it all based on the ply. So you can see here when I zoom in, we have many thin plies here and some thicker plies, and you can see all these different plies layered. And if I go through and start isolating some of these plies, you'll see that these plies have a specific shape, and normally in zone-based modeling, you'd have one zone which represents all of a specific area which has all of the same plies. And so in ply-based modeling, you're basically going through and keeping all the ply entities and just representing one card that kind of defines the entire laminate. And that's called our stack card, and you'll see it here underneath this laminate feature. And so basically that's the two kind of differences. In a ply-based modeling, you'll have many plies and one laminate card that will kind of tell you the order that all your plies stack up. And in the zone-based modeling, you'll end up with lots of properties, and each property is grouped to a separate set of elements. And so each one of these color zones has its own property card. And that gets a little bit difficult to manipulate when you're changing all these different plies, because you have to go through and update every single zone that uses a specific ply. So today we'll be working with analysis and optimization on a ply-based model, and it will be this model. And so just so you guys kind of understand the process, optimization with our Altair products is broken down into three main steps. The first step is going to be free size, and this is basically going to tell you where you need material and where you need thinner material, where you need thick material and where you need thin material. After you run a free size, what we'll do is start cutting up all these different layers into thinner layers and starting to realize actual ply shapes that would be manufacturable. From there, the last step is a shuffle optimization, which basically tells you which order to lay all your plies up. When you start out with a model, you're probably going to come and bring in some type of CAD from some other modeling software. And so we want you to get to a point where you have mid-surfaced your CAD and have a nice clean mesh on the part that you're going to be looking at. So today you can see we have that as our starting point, and we also have kind of the frame here as modeled as 1D elements with some rigid connectors attaching the two. So this is the model we'll be working with all day and kind of going through the whole process of what's involved with analysis. If you look, when I bring in my model, we have a couple of different components. Like I said, tubing, the monocoque, rigid connections, and then some insert plates. We also have some loads and single point constraints. And then we have our two load steps created. So right now, everything in this model is set up like our traditional linear static analysis, but we haven't actually created any material properties or plies for our composite layup. So in order to do that, all you have to do is we'll start with our materials, and we'll right-click on material and click duplicate, and that will bring up a new material. So in this case, we're going to make our carbon material. And in most cases, when you're dealing with woven materials, you'll be dealing with a mat 8. So you'll have anisotropic properties, and so these properties will be, from either a supplier or from some type of data on the carbon material that you're using. So we can go ahead and start putting in some of these values, and these will be specific to the material that you're using. But I have some values that I'll put in here, and basically going through these, you have a Young's modulus in your principal direction and a Young's modulus in your minor direction. And then you have your Poisson's ratio, and you have your shear, and you have your density, which should be here. And again, if you're familiar with HyperMesh, this is a unitless preprocessor, so all of these units will have to be managed by you, and make sure you're putting in the right units. Down here, these values, this XT, XC, YT, YC, these are going to be your failure criteria. So these are essentially your yield criteria for your material. And so you'll have tension and compression in the X or primary direction, and tension and compression in the secondary direction. And so these are helpful if you want to look at, failure values in your model. And then finally, S is your shear failure. So now that we've set up one material model, that's going to be the carbon fiber that we use, and we'll also create another material model. And this one is going to be for the core. So many times when you're working with composites, you'll have a core of some type of foam or cellular structure, and then you'll have composite layup on top of it. So we'll go ahead and fill these in really quick. And again, here you have the same failure criteria, so you have tension, compression, and shear. So once you've created your materials, we're going to check the orientation and normals of our shell before we start creating our plies. So in order to do that, we'll go to the Tools panel and click Normals, and select our component, and we'll ask it to display the normals. So you can either display the normals as arrows, or you can choose to display them as colors. So if you look, when we display all these normals, all the arrows are pointed in the same direction. And so basically, we're just making sure that we don't have flip-flop normals within our model. We want everything to be facing the same way so that when we start building our material, everything is continuous. The other thing that we want to check is orientation. So in the Analysis panel, if you go to Systems and Material Orientation, you can select these elements by collector, and you can review their orientation. And if you zoom in, you'll see that there's little arrows that are placed on these that basically tell you which direction all the material is going to be laid on this. So this is a reference direction for all of your orientations of your plies. And just to be safe, you can go ahead and assign an orientation. So if you select these elements again in this collector, and you select a system as your base system, and click Assign, you can see that all these elements were assigned the material orientation, and they're all in the same orientation now. So once you have your orientation in your normal direction set, we can start creating plies. If you right-click in the model browser, go to Create and go down to Ply, you'll see this Create Ply window pop up. And basically, in this, we will create a name for our ply. So we can create Ply 1, and our card image is set to Ply. Your material type, you'll select the composite material that you chose. You'll give it some defined thickness, and then select the orientation. So you'll go through these, and you'll have to select the elements that this ply is going to be applied to. So when you click on this shape, you'll bring up this selector, and to start, we're going to select the entire model as our design space. So the idea is this model that you have here was designed, whether it's for aero or for some other reason, we want to start with this shape, and we want to tell it that it can use any material, any ply orientation on any of these elements, and we want to give it as much design freedom as possible. So we select all the elements, make sure that this output results is checked so that we can view the results when we run our analysis, and click Create. You can see here that the name updated, and we can go through and create a new orientation. So -45. Select these same elements again, and click Create, and now we have another ply that's created. So you can go ahead and go through that and create all of your plies for your different orientation angles that you want to look at for your either your design or your analysis or your optimization. And after you create all the plies and their different orientations that you want to look at, we'll have to create a laminate. And so the plies are basically individual entities, and the laminate is going to combine all the plies to create your final composite laminate. So again, right-click, go to Create and Laminate, and then we're going to name our laminate, set the card image to stack. Usually when you start off, you'll want to use the smear core option. So all these different options have different effects on the way that you do this. For this case, actually, we're going to use the symmetric, which basically means that when I put in my plies in here, it's going to mirror them on both sides of the plate. And you just have to go through and select the order that you want your plies to lay up in. So once you select all your plies and click Create, you can close this window, and you'll see that we have a new laminate that was created. And so what we want to do is create a property card for this ply, or for this component. So the last step after you've created your laminate is to create your new property. And in this case, we're going to be using a card image P comp for composite, P for ply. So P comp P. And in here, again, there are some other settings. So if you want to set a Z offset, or you want to use some type of failure criteria, you put in your failure criteria, and this SB is going to be your shear between layers, so your bonding shear. And so you can put those values in. And so once you go through and create this whole laminate, I'll just pull up a completed model here. And you can see I went through and I created 4 plies, 4 different plies, the 0, 45, -45, and 90. I have my core, which is made out of another material, Rococell, and then I also have my insert composites. So these pink inserts here are going to be made of composite as well, and they have 4 composite layers, different angles, and then they have an aluminum core. So once you have all these created and you have your Plies created, your laminate created, and your property card, you can use these visualization options down here to turn on both 2D representation or 3D representation of your 2Ds and the composite layers. So when I zoom in here, you'll see that I have kind of an all blue thing, and if you look really closely, you can see all these, and that's why it's really helpful to make sure that you auto color your plies or change the color of your plies so you can differentiate between them. And when I zoom in now, you can see that I have my core ply and then I have my 4 outer plies, and you have that on both sides due to the symmetric property in the laminate. So that's pretty much the basics of setting up a composite for analysis. So if you're working with some type of CAD software where you've already designed a CAD product, you can actually directly import your plies and all of this and realize them in HyperMesh for your analysis. And what we've done here is basically the traditional setup for an optimization. So we don't have any ply shapes defined really yet. We just know the total shape of the component, and then we know, the different orientations of fabric that we want to use for our composite layup. Right here we have a simple loading case where we fix the back wheels, and we're applying some forces on here. We actually have 2 different loading cases. One is a torsion one way, and the other is the symmetric torsion the other way. So what we can do now is go through and run this analysis. So from within the analysis panel, if you select OptiStruct, you can basically pick a file and write in the name of your file and click Save. And then when you click OptiStruct, it will launch the analysis, and you'll get a window like this, and it will go through and run your analysis. So I've already run this analysis, but it only takes a couple minutes to run. And so I just wanted to show you the results. So what I've done is I've created a new page in HyperWorks Desktop, and I've loaded up the HyperView profile. Within that, you want to open your results, so you can either do File, Open, Model, or you can click on the Open Results tab here, and you'll browse to the folder where you ran your analysis. So if you're not familiar with OptiStruct, there's lots of files that come out when you run an analysis, but what we're really focused on is this H3D file. So this is where all the results are contained from our analysis. And what you'll get is something that looks like this when you bring in your model. And there's a couple of different ways that we can look at it. And for composite, it's really nice to make sure that you look at the different stresses and strains throughout all the layers of the elements so you can kind of understand that. These are all output options that you can select when you're creating your deck. Real quick, I'll jump back and I'll show you guys kind of where those come in. So when you're creating your control cards, you have these global output requests. And so the main ones that you'll want to focus on are the C strain, which is composite strain, and C stress, which is composite stress. And to have these all in the same format, we'll select the H3D format for both of these. That way, if you do that before you run your analysis, you'll have these values to look through when you're looking at your results. So if we just play this animation, you can see in subcase 1 we have a torsion one way, and in subcase 2 we have the torsion the other way. So if I want to contour this with my composite stresses, I just select composite stresses, click on my component, and click Apply. Ooh. There we go. I reran the analysis there, so I had to reload it. So we'll look at our composite stresses, and the nice thing about using Hyperview to look at your composite analysis is that we have all these layer options. So by default, it's set to max, but you can look at all these different values, the sum, and click apply. You can look at individual layers. So if you have, your minus 45 layer, you can look at what the stresses look like in that. You can go through all these different layers and look at the different stresses in these. And then there's also an option called extreme layer, min layer, and max layer. So these are going to tell you which layer your max, min, or extreme values are in. So you can see here these different regions are color-coded, and if you look at the legend, it will tell you which ply of your composite is actually seeing the max value of von Mises stress. So this is helpful to understand kind of which components or which plies are important in your component and which areas that they need to be. So again, there's lots of different options for contouring, both composite stress, composite strain, all the different values. So we can see here that my max strain is primarily in my my core here, or the 0 degree, I'm sorry. So you can see those shapes. And basically this is our baseline analysis. So this is telling us where we're going to start when we work on our optimization. The first step of the optimization, like I said earlier, is going to be your free size. So in order to set up a free size optimization, we'll go back to our original deck and we'll use this optimization panel to start creating the free size. In order to create our design variable, we'll just click on free size, put in a name, select the property that we want to, So we'll actually select stack and then select the stack that we want to optimize. So in this case, we're going to do the CFK Roca stack and click select, and then you just click create. So once you've created your design space, you're going to go through and look at the different parameters. So on the parameters page, you have minimum dimension, which is basically if you think of having ribs or some type of struts in your structure, this is going to be the minimum for that kind of structure. You can put on stress and fatigue constraints. And then under composites, we have, this is really the section that's important to composite design specifically. You have your minimum and maximum thickness for your overall laminate. So this is saying here we have 2 millimeters is our minimum thickness and 25 millimeters is our maximum thickness. And then in this box over here, we have all of our manufacturing constraints. So one manufacturing constraint that's really important to us is the balance constraint. So that's going to make sure that whenever we put a plus 45, we have a minus 45 to go with it. This is going to reduce any of the unwanted moments being created in our model due to unbalanced layup. As we go further in the optimization, we'll start adding more and more manufacturing constraints, but when we start out, we're going to leave just the balance constraint. Don't forget to hit update whenever you make changes in these panels. So there's more options here, but we'll go through and we want to look at the responses. So whenever you do an optimization, you need responses that are basically going to be what the optimization is working with. In this case, we created a weighted compliance and a mass response. So the mass response is going to tell you the mass of the structure, and the weighted compliance basically works by looking at the compliance or the stiffness of a structure in multiple load cases and scaling them. So in this case, our two load cases are equal and symmetric, so we're both scaling them by 1. But it's important that if you have load cases which result in different stiffness values, you want to scale them so that they're all similar in value. That way it won't bias any of the different loading cases. So once we create our responses, we'll need constraints, and our constraints are created in this design constraint. And so in this case, we put a constraint on our mass. So we wanted a mass of our structure to be 50 kilograms or less. And so we put this upper bound, we select the response as mass, and we click create. And finally, we want an objective. And so our objective is to minimize compliance. So compliance is the inverse of stiffness, and so we want to get the stiffest structure. So we're going to minimize our compliance. You click create, and that's all you have to do to add a free size optimization on top of a running analysis, composite analysis. So it's a pretty simple step, but you get some pretty interesting results. So you go through the same process of running it through the optimization panel, or you can write out the deck and run it through OptiStruct manually. But once we run these results, we'll get a couple of different files. I'll open this up right now just to show you kind of all these files that you'll be getting out of here. So it's a long list of files, and what's really important to us are this _des.h3d, which is going to contain the design changes from the optimization. And then you have these S1 and S2.h3d. These are going to actually contain the results to the subcases, so subcase 1 and subcase 2. So here I've created another page with 3 windows where I've opened up all of the H3D files. And really we're just going to focus on this design file right now. So this is the _des.h3d. And when you open this up, it will look just like your model, but underneath the contour panel, you'll have some different options. So here we have composite manufacturing constraints, element thickness, orientation thickness, and then ply thickness. So if you look at element thickness, this is going to give you a contour for basically where the overall laminate thickness is. So here in the red areas we have 25 millimeters, and here in the blue areas we have 2 millimeters. So basically this is showing us that this is where the structure needs to be. But Hyperview can do more than that, and we can actually drill down into individual plies. So if you change this to ply thickness and go to your filter or your layers, you can select an individual ply, and you can see the thickness breakdown for that specific ply. So here, you know, we need about 1 millimeter, and here we need only 0.2 millimeters. So this is really nice. You can drill down and really inspect all these different characteristics of your analysis. So this is our design, and you can look through all the different iterations. So sometimes it's nice to see basically how this optimization ran and what it got to. So if you look here, we started off with the entire model being about 5 millimeters thick, and we went through the optimization and it refined, and it found the optimum thickness here. In general, this is going to be, you know, a good starting point to understand where your model is, but this still isn't something that we can really make, so we need to do a little bit more analysis. And so that's where the free size, or the size optimization comes in. So if I go back and I look at my deck, this was my free size optimization. And so OptiStruct has a really nice feature where you can actually tell it to run a free size optimization, but then also set up a size optimization for you on the other side. So inside of, on these control cards, you can go to the output control card, and you select this free size to shape as your keyword, and then you're going to set your frequency to yes so that it does it. Basically what this will do is when you run your analysis, along with all those other files that we had, the H3D files that we looked at, it's also going to write out a new FEM file. So here we have free size and then _sizing.15.fem. And so what that has done is it's actually taken our free size optimization and broken it down into more plies so that we can start doing a size optimization on it. So here I've opened up that FEM or input deck into HyperMesh, and we're just going to look real quick at what the differences are between the original deck that we had. So originally we had 4 plies for the main composite and 4 plies for these inserts. But now you can see plus the core plies. So we had 5 for each. And so now you can see that the inserts haven't changed because we weren't running an optimization on that. But now we have all these other plies that were created. So by default, that free size to size setting will create 4 plies for each 1 ply that we had before. And the way these numbering schemes work here, you'll see that it has the first number is representing the design variable. So these are all 1 because they're working on the same design variable, which was this entire composite component. The second number is going to be which ply it's referencing from the last model that we ran, so from the free size optimization. And then finally, these last 3 numbers are the new ply identification numbers for this run. So we have 100, 200, 300, 400, and then that is all representing design variable 1 and ply shape 1. So if we go ahead and isolate these, what you can see is we have 4 plies which used to represent, or which represent what was 1 ply before with variable thicknesses. So we basically cut it up and said, you know, all these different pieces have different thicknesses. So if you look here, this red part has 5.4 millimeter thickness. This has, 0.09. And then as you drill down, you can see basically we've cut down the thickness into all these different layers. And there's 2 of them, and they show up because of our symmetric property. So once you run this, you get this new input deck, but it's not very clean. So you have lots of random elements floating around, lots of holes. So what you're going to want to do is go through and actually clean up your model. So by doing that, you can go through and edit, select elements, and you can go through and just go remove elements that you don't want to be in this model anymore, or you can add new elements. So you can go ahead and do that. When you click proceed and update, and we look at this now, you can see that our shape now doesn't include those elements. So this is the point where you go through and clean up all your elements so they're much squarer. So here I have an example of a model that's already been cleaned up, and you can see here all these are fairly nice shapes. And our last step that we're going to look at is we're going to run our size optimization. So once we have all of these set up, we're going to create a new design variable for free size and go through creating these. So, composite size. So we're going to do our size, pick our laminate that we're working on, and update these manufacturing things. Again, there's a setting in the control cards to go through in the output. Instead of free size to size, we're going to look at size to shuffle. So this, once we run our optimization, will get us all ready to go for our shuffle optimization, which is the last step. It's suggested that we run this through 2 steps when we do our size. So we do a first step where we do continuous size variables, and we do a second step where we do discrete size variables for the thicknesses of our layers. So that's important because basically when you do manufacture this, you're going to have a specific thickness that you have in each sheet, and that's where this T manufactural comes in. So this is basically going to be the manufacturable thickness for your models. Once you have that set up, you'll see that all of these plies have 0.1 millimeter thickness, and then these core plies have a manufacturing thickness of 1 millimeter. So that's all set up, and we can run our optimization, and what we get out of that is a free-sized model. So if we look at each one of these plies, you'll see that the thickness is either 0.1 or some multiple of 0.1. And so this basically gives us a model where it has been optimized for not only where these plies should be, but the shape of the plies and also the thickness of each individual ply. And so this is now something that we can manufacture. And the last step is to run our shuffle optimization. So again, in optimization, we will create a composite shuffle, give it a name, and then here we can put in more manufacturing constraints like our pairing or the number of core, or the representation of which plies are our cores, and we can also put a cover if we want specific plies on the outside edges of our model. So that optimization, once you run that, you'll get some results that are basically a table that looks like this, and they will tell you, which ply numbers you should lay up and in which order. So here you have all of your ply layups. You have your 90 degrees and your 0 degrees, and we set up a pairing between the 45s and the minus 45. So you'll always see a plus and a minus 45 next to each other with these yellow and green colors. So that's a really high-level overview of kind of composite optimization and analysis using HyperMesh, OptiStruct, and HyperView for your post-processing. So there's a lot more capabilities that we didn't go into a lot of detail here, and you can get into a lot more complex types of analysis. But we really just wanted to make sure that you understood the basics of the procedure and kind of got familiar with some of the different names and the steps that we go through here. Real quickly, I'll just show you this kind of overview of the optimization. So we have our initial model, and we have our compliance here and the mass on top. So you can see our initial model started at 66 kilograms and had a compliance of around 1.5 e to the 3, or e to the 5, sorry. And as you go through each step, you get a little bit lighter, and you give up a little bit in compliance so that you can make something that's manufacturable. So you can see here in our last step, this is our final design. And so all of this material and a very detailed tutorial on this is available on our website. So if you go to altairuniversity.com and click on the academic program, you'll see a lot of links that will be helpful. Again, the free student edition is available here. You can look at free books, and we have our support forum, which is where we encourage you guys to talk to each other, and we have Altair employees that manage that can help you out answering your questions. But underneath learning, we have the training center, and under composites, we actually have the full tutorial, and all the model files that I've shown you today are available, so you can go through this on your own to really dive deeply into all these different facets of it. So that's pretty much all that I have here today. We have a couple of quick polls that we want to open up. So before we open those polls, though, we want to just open the floor to any questions.
All right. Okay, so can you hear me, Andrew? Let me make sure I'm okay. So Andrew, so thank you, and thank you for showing where the academia information was at and where to get the tutorials here. And there's a wealth of other ones. We do have a couple questions, and let's go over those. So the first question is how are you include the variable core thickness with many different components? Okay, so not sure if that's easily to understand, Andrew, but so how are you able to include the variable core thickness, many different components? I'm not sure, is that clear enough for you, Andrew? Okay.
So basically the way that the core material works in this analysis is that we are allowing it to be a variable of a specific manufacturable thickness. So if you imagine you have 1 millimeter thick core material, you can put 3 or 4 layers of them. So when you start off, it's a completely continuous kind of variable, but as you get down through the optimization process, you discretize it and basically come up with a single thickness. You could also do that. You could constrain it to be one specific thickness throughout the whole optimization if you have a very specific core material that you want to use and you only want one section of it.
Great. Next question. Is it possible to include a buckling analysis in the load steps considered in optimization?
Yes, so you can include buckling analysis, but the buckling analysis is going to be specific to the global performance. So you can do any type of analysis that we support with our composite cards during the optimization. But again, it's going to be based on the global performance. So if you have, it's something that, this is basically the optimization is working on a higher scale. So if you're looking at individual micro level, we have other partner programs and other capabilities to look at that, the smaller levels of the composite behavior.
Okay, and that's also a good point if they do need more assistance. When we ask the polling questions, we can go from there too. With the unfortunately, with the student version, the partner programs aren't included as of right now, so just something to be aware of. So let's move on to the other question. So if you could, please provide some more information regarding the optimization method you are using.
So the optimization method in OptiStruct is a gradient-based optimization. So if you go in here, there's more details in the actual manual, but there's a couple of different optimization methods that you can select from. So by default, it will choose which one is best based on the type of optimization, and it's using MFD for this one. If you want more information on that, again, you can find it in the manuals, and you can also, ask on the form if you have specific questions about, what more detail on those different algorithms.
And also to add that when you do get the student version, you will have all the online help links there too, so the manuals will be something you can search there and get information from. All right, next question. How could you exclude suspension links from results?
Yeah, so if you didn't want to include the suspension links in your analysis, you don't have to build those in. You could apply these forces, directly at the connection points. If you want to view your results without the connection points in there, you can do that in Hyperview. Let me pull open a quick session here. And you can simply turn those off if you don't want to view them. So if you didn't want to see these other parts, you could turn all those off and look only at, the part of interest in Hyperview.
Good. The next question is the composite optimization process based on density method, such as for topology optimization?
So we are not doing a topology optimization. So we're doing a free size optimization. So basically the design variable that it's looking at in the math is the physical thickness of each element. So it's basically going into the property card, into the Ply card, excuse me, and varying that thickness on a per element basis and kind of going through it that way and finding the ideal. So it's not a density based, it's actually a thickness based. So it's working on the properties.
You're right. Is it possible to optimize the shape of the monocoque? Say I know I have the free reign over the top cover shape, like any morphing optimization. So again, is it possible to optimize the shape of the monocoque? Say I know I have a free reign over the top cover shape.
Yeah, so basically what you'd do in that case is you'd start off with a topology optimization. So you'd tell it all the space that was available and the loading that it's going to see, and then design, run a topology optimization, which will try and tell you where the material is needed and where it isn't. So from that, you'd have to go through and come up with your design. On the other side, if you wanted to do, you have a general shape that you want to work with, you could do a shape optimization where you morph it between all these different shapes and use those as variables, which you can then go through and run an optimization on those. So if you wanted to just find, the ideal shape for the structure just by varying these, morphing different areas, you can do that as well.
Great. Next question, is it possible to use your software as a solver called externally by another program, let's say MATLAB?
Yeah, so you can call our solver in, let's say, batch mode, so it runs basically in the background. It runs on command line, so basically if you can access the shell, you can run our software and you can generate our input decks and push and pull them using other softwares.
And I'll just add to that, on the online help, there's just a section there how to run our solver from the command line, so that would be the variables you need for that. Next question, what are control cards?
Yeah, so control cards are an entity within the deck that it basically looks at. So your control cards are a line in the deck that tells the solver what to do. So there's lots of control cards that basically manipulate the outputs and the different inputs into your deck. So these are all specific to the solver.
So every solver will have different control cards depending on what they run. In this case, you're just showing the OptiStruct ones, correct?
Correct.
Excellent. All right, so next question, does shuffle results apply for a single property? In the broadcast, it showed the results for stack 1, so in case of more stacks, are there going to be more ply orders?
Yeah, so if you have multiple stacks, then you'll have different outputs for those. So you'll have to run an optimization on each stack, essentially, and you'll get different results for each laminate that you're optimizing in that shuffle phase.
Great. Next question. Was the SB parameter you set before the inner laminate shear strength, is it possible to detect delamification?
Yeah, so the delamination that is used is basically the shear between layers, and yeah, so that's if we look at our results, let me see here. Oh, I didn't output the failure, but you can look at both the failure in the composite layers, and then if you put in that SB value, which is the shear of the bonding between the layers, the maximum shear stress, then you can also see the failure in the bonds between layers. So yes, you can do that.
Right, fantastic. Is it possible to write your own script routine, your own optimizer, and run it using your software?
If you wanted to, this kind of goes along with the MATLAB question that was asked earlier. So if you wanted to write a MATLAB script that did some optimization and went in and manually edited the text file, the text deck, the input deck you could use some external software to then modify the input decks and run them through our solver by running it through the command line.
It sounds like an advanced form of coupling two solvers. Okay. All right. Right now we're out of questions. Are there any other questions people would like to ask Andrew? What options exist for improving prediction of failure stiffness of inserts in sandwich structures?
So I'm not sure if I'm exactly understanding this, but in this case, we're looking at kind of a linear view of all of these. So we're looking at basically if the these shear stresses or these tensile stresses are greater than some yield value, and we're not actually really in OptiStruct getting into the detailed failure methods of these sandwich structures. We do have software in Radios. We do sandwich structure failure and delamination and more detailed things like that. So if you're interested in that, that's definitely something that you should look into, both in the forums and through our documentation.
You mean also the additional training material that we have there too, correct? Excellent. Well, great. We've have one more question, and then we'll close up for today. So, is it possible to define an existing shell as a laminate inner or outer skin rather than being a laminate midplane?
Yeah. So basically, that option I'll show you really quick, just because that's a very good question, especially if you have a specific arrow requirement on the property card that I created. There's the offset option. Let me load one up really quick that you can see the plies. So you can see all my different plies, and if I do a 3D representation, you can see their thicknesses. Right now, they're symmetric about this midplane, but if you change the setting in the property for this laminate to, let's say, top, you can see when I refresh this window, oops, that they've all shifted down. So now they're at the top of the surface. So this red surface here is actually at the plane where the geometry is. And so the whole model is offset. So these options, both top, bottom, and then real, you could specify a specific value to offset all of your laminates from.
Excellent. One more question came in, and this will be the last one. And we do appreciate your interest, and that's why we'll have one to pull in questions if you would like to contact us with some, other specific needs, training, and so forth. Or, and as Andrew said earlier, too, the support form on the academia site is also a place to ask questions too. So this last question is it possible to solve coupled problems, for example, thermal and structural?
Yeah. So in OptiStruct, we just added the feature, I believe, to do thermal analysis on our composites. It's something that's new. It's not in any of our 12.0 releases, and I'm not sure if it's in 13 or if it will be in our new release this year in 14. But that's something that we're looking into, and is being developed currently.
Excellent. And the current version of the student copy is based on version 13.0 that was released last year at the end of the year. So 14.0 is not targeted to come out till again end of this year. So just sort of for a reference point. Also, I want to add. I did put the link up there just in case if people weren't able to capture it when Andrew was showing it, but the link for the academia site and the program where you can get free download, links to the free books that we have, to FEA, practical aspects of FEA, some optimization, multi-body dynamics, and so forth. So again, thank you so much. We're now going to start the polling questions here. So just give it 1 second for those to come up. So the first question is, would you like a member of our team to follow up with you for further training? Again, this would be for your full team or your department. This would not be individual one-on-one training, but for your whole department or team. And we'll give everybody about 30 seconds to answer that question. And even if you know you don't need any, you can just select no for now. Okay, great. We'll move on to the next question. And for us, we like to conduct these and some other topics. For instance, we have a software called Virtual Wind Tunnel that a very user-friendly interface to set up your model in a wind tunnel. That again, it follows a similar structure that we use for Inspire, another product, which again is a very user-friendly interface. But there'll be other topics we'll be interested in doing. So we want to know when's the best time in your next build phase or planning phase that we should conduct these. So the options are on the screen there. Excellent. Thank you very much for taking the time out of your schedule to see this session and also to answer these questions here. Again, I hope you ever enjoyed it. And again, please review our academia site for additional material that can be of help. And have a great day. Thank you, everybody.